Hope all of us are doing great. My name is Ernest, and this is the Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at a concept under the moments of inertia. And basically, this is going to be concerning an area which is going to be, of course, indicated using the two Cartesian coordinate system of x and y. And of course, we're going to borrow from our last discussion where we had looked at the concept of a moment and basically defined what a moment is. And in a summary, I can give this one as the rotational effect of a force about or the rotational effect of a force on a body about a fixed position. And that basically gave us a concept of this specific concept of a moment of inertia, whereby we had given it in terms of an equation. So basically, I described this one as the product between this basically the moment of inertia is the product of the total mass and but basically the product of the total mass and the square of the distance from the center of rotation or that fixed radius. Now in this particular case, we shall look at this specific point of the moment of inertia with respect to the y and x axis, and I'm going to use these two specific illustrations for A and B in trying to evaluate this particular aspect of the moment along the x and y axis given using those examples. Now this is going to be relevant for us since we had mentioned from our first video that this basically concept of moments of inertia is going to be very much applicable in our subsequent discussions. And we had said that basically for us to determine how our device is going to hold up to external and the internal forces, this is going to be one of the ways in which we are going to evaluate this aspect of the magnitude of the force. And it's also going to be handy in trying to assist us find the angular momentum in some of our discussions. And last but not least, we're also going to be finding a way of analyzing and predicting rotational motion of various objects which we are going to come across. Now in this particular case, then therefore we had mentioned that we can find the moment of inertia about the x-axis using this specific integration procedure, whereby we said that this is going to form the integral of the square of y and the dA. And I had mentioned in a sense that we are going to consider, if we're going to find the moment of inertia about the x-axis, we're going to consider an area element in the x-axis, which is going to be defined by a small change in x and a small change in y. And this basically is going to give us this concept of an area which is going to be given in terms of a dA. So therefore, we had mentioned that dA is going to be the product of dx and dy. And that's going to form this specific element of the integral part of this specific aspect of the moment of inertia. So from that specific point, then therefore we can find the summation of this specific product of the square of y and dA in order for us to find the moment of inertia over the x-axis. And in this case, perhaps I can just give it in a small summary, whereby we said this element of dA is equivalent to dx over dy. So I've of course explained on this specific product and how we can obtain it. This is obtained by choosing a small area element in the xy Cartesian coordinate system as I've illustrated on the board, and therefore we can give this moment of inertia about the x-axis as the integral of the y, the product of y and this specific aspect of our element of dA as I've just given as such. So similarly, we can find the moment of inertia about the y-axis given in terms of this specific product as the integral of the square of x, and then we're going to have dA. So in this case, this specific aspect of dA is still going to be having the same implication as the one which we have given on the board. And therefore, it's going to be pertinent for us to try and find an evaluation of this integral by trying to choose this specific aspect of dA along the respective axes for the x and y. And I'm going to use perhaps an illustration in trying to achieve that one, and then therefore we're going to basically try to do an evaluation. So in this case, we're going to have this specific element as given. So if we are required to find the moment of inertia along either the x and y axis, we're going to choose a small area which is going to be defined by dx and dy as I had explained. So this is going to form a product of dA. So in this case, we are going to see that this is going to be the x and the y-axis given as such. So for us to consider the moment of inertia either along the x or y axis, we're going to consider that specific, of course, product which we're going to have at dA is equivalent to dx and dy given as such. So in this case, this is going to be forming our change in y. So sometimes we're going to give this one in terms of y given as such, and the stretch along the x, we're going to give it in terms of x as such. So for us to do an evaluation, as I've said, we're going to find a specific integral which is going to be given using this specific aspect of a dA, and then we're going to be considering this specific aspect to be a thin strip parallel to the axis of course, a preference. In this case, we can give either this specific aspect. So in case we are going to consider this one for the finding the moment of inertia along the x-axis, we're going to consider this specific strip using the first illustration which I've given on the board, whereby we're going to choose for the total area which I've demarcated in this particular case, we're going to choose a small strip which is going to be parallel to the x-axis, which is going to be, of course, the area bounded by the surfaces which we can define as a b dy. So this is going to be the area of the product of a b dy, which is the difference between the difference between this specific point, initial point, to this one and this one, and therefore the shaded part is going to be the strip of a preference which we're going to choose. So for us to find this specific moment of inertia, and therefore along the x-axis, this is going to be given as the integral of y, the square of y dA, which is, as I've said, the square of y dx dy given as such. And of course, if we're going to look at this one, we're going to have this specific aspect of the change in x given in terms of b. So therefore, we can have this one given in terms of the integral of the square of y b dy given as such. So for us to find this moment of inertia, then therefore we are going to perform an integration, whereby the moment of inertia along the x-axis can be given in terms of, so b is going to be a constant in this specific case, and then therefore we are going to have to do the integral of this specific y, which is going to be y to power 3 given from this specific point of 0 to h given as such. And that is going to give us this specific, of course, a moment of inertia along the x-axis, as I've indicated using this specific, of course, point for rotation. That is going to assist us in the direction which we are going to define this specific moment. So therefore, this specific integral is going to be giving us that particular evaluation, whereby we're going to have this moment of inertia given as the product of bh squared from this specific integral all over 3 given as such. So this is going to be giving us our moment of inertia, of course, along the x-axis, by considering this specific small strip for the rectangular area which is defined by this specific boundary which I've given in terms of blue. So similarly, we can find the moment of inertia about the y-axis by using the procedure which I've basically used for the concept of the moment of inertia along the x-axis, by giving us as the integral of the square of x dA, which is basically given as the integral of the square of x dx dy. And in this case, we're going to choose our a specific aspect of h, which is going to be our constant, and therefore we are going to have this specific aspect of dy given in terms of this aspect of h. So therefore we're going to have this integral given in terms of the integral over x squared h dy given as such, or h dx basically. So I've chosen y, the aspect of y. This is going to be a rotation along the y axis. So therefore we are going to define this one using this specific aspect of a strip chosen as the difference over dx, and therefore we are going to have this specific aspect of a dy chosen in terms of the h which I've given. So therefore we are going to have this one given in terms of the integral of the square of x given as such, dx. So this basically is equivalent to x to power 3 over 3, and then we're going to have this specific aspect of h. So we had h given as such. So h is going to form our constant, which is going to be brought outside the integration sign, of course, and this is going to be forming our integral between 0 and b given as such. So I've just given this specific stretch which we are going to consider, and therefore this is going to be given in terms of h, which is a constant, b to the power 3 over 3 given as such, and that's going to be giving us the moment of inertia along the y-axis, just using the similar procedure using the first example for a and b given as such. So whenever we're going to come across any of the evaluation which is going to require us to find the moment of inertia of an area with respect to x and y axis, we're going to consider the two formulae for this one which I've given, and this one which is going to be given. So in any case, we are going to see that for us to find the moment of inertia along the y-axis, we're going to consider the square of x and dA, where dA is the area element. And for us to find the moment of inertia along the y-axis, the x-axis, we're going to consider this specific square of y dA, whereby we're going to use this specific aspect of the area elements in trying to define those two specific aspects as I've just indicated using my figures to the right. So kindly check our description boxes for various links of other videos. Subscribe and engage us in the comment section, and also ring that notification bell to be getting updates on our various aspects we do in mathematics and sciences. So that is it for now, guys. Bye, God bless you. Catch us in our next video.